That's for me, so I know that it's not honors when I look later. Okay. All right. What? So we had some problems we were starting last week, right? On Thursday. You have no idea. Hannah, you weren't here? All right, then I won't look at you. Who was here on Thursday? We did some problems, right?
Yes.
There were 2 problems that we did. We didn't get through both of them, did we? We didn't get through B, did we? No. We got through A, correct? Yes, it's on the portal. Did you look on the portal? You should, not the portal, the YouTube channel. Look at my YouTube channel and watch those videos.
Check me out.
You thought about that? That's good. That's a good start. Thinking about it's a really good start. But what would be better is if you actually did. That's great, Hannah. I know you're like, aren't you proud of me? Not really. That's great. Yes, we're on problem B. So problem B, if I'm not mistaken, was a ball on a ledge, right? Okay. How about you think about sitting down and paying attention? Oh.
You got you.
Okay. Here's the ball. Okay, and the ball, we push the ball off and it goes straight down, right? Okay. Isn't that a nice tool? I do like this.
It's like smooth, but it's perfect.
Yeah. Okay. Well, I gave you a height, didn't I?
Yeah.
Does anyone remember the height?
Yeah, it was actually. You didn't give us a height.
I must have given you a height.
No, you didn't.
I gave you some time. I was looking for height, but gave you time.
No. How long will it take to travel? Was it velocity of the Y? You said it's a free fly.
Okay, what was the okay, the first question was what?
What's the velocity?
3.2 seconds, where is it?
I'm sorry,
After 3.2 seconds, where is it?
so delta distance after 3.2 seconds, right? The change in distance, where does it go? Okay. And then, what was the next question?
The other was how far will it go, or no, how long will it take to get a certain distance?
Okay, so the delta time, it takes to do what? Negative, delta time for the distance, I said, or for delta distance?
How long will it take to go with negative 52 meters?
52 meters. Is that clear?
What?
Chris, oh, look at that, nice. Okay, all right. So we have this change in time for our distance to travel negative 52 meters, right? Now our delta distance after 3.2 seconds, what is our delta distance, question mark, and delta time, question mark, right?
What does that say?
Carmen.
Does that say 4?
4, delta D. Delta, let's see,
What does that
meaning, what's the time it takes for the delta distance to go negative 52 meters? For me to travel negative 52 meters. Yes, this is question B from last week. So, what does that look for? All right. Okay. So when we're doing problems like this, there are a couple things you've got to do. There's a couple things look at that. Look at the wall over there, right? We've got our problem-solving process, right? What's number 1? Draw a picture. Have we drawn the picture? Okay. What's the second thing? Lay out our facts. So what is it we know about this scenario? Okay, well, do we know the delta distance? We don't.
Oh, I was going for number 2.
Okay, so all right, so let's in general, before we look at each one specifically, in general, what do we know about this type of motion? What kind of motion is it? Constant what? Why is it constant acceleration? Okay, and what is causing it to do that? Gravity. So gravity is pulling on it, right? And gravity is a force, and it's causing it to accelerate. Okay? And so we're trying to use that acceleration that's due to gravity, and that acceleration, and what does it mean when we say that we're accelerating? What does it mean if I'm accelerating? Okay, if I'm accelerating,
Then that should be speaking.
I'm just speeding up. If I'm accelerating at a constant rate, then
Speaking up, but it's not.
speeding up at a constant rate. Okay. So the acceleration due to gravity is what? Do we call it?
Not 10. Negative 10.
Negative 10 meters per second. Okay? That is the acceleration rate squared, excuse me. That is the acceleration rate due to gravity. Notice it's got what sign on it? A negative. So that tells me what? It's pulling me downward. Okay, the magnitude will increase. The magnitude of my velocity will increase, but it's in the downward direction. Yes, ma'am.
So it would only be like positive, in the like vertical sense, it would only be like positive acceleration if something was going up like a rocket or something.
Okay. Well, here's the thing. Okay, so let me ask this question. I take the ball and I throw it up.
Yeah.
Let's talk about 3 points. When it leaves my hand, when it reaches the top, and when it lands on my hand. One between leaving my hand and the top, is it accelerating upward? Is it accelerating at all?
No, it's decelerating.
It's decelerating because you know that because my velocity is what? Decreasing from the point of my hand up to the top, right? So it's decelerating. So is it accelerating when it leaves my hand?
No.
Well, it's accelerating in a negative way, but it's not accelerating upward. In order for it to accelerate upward in a positive way, I have to overcome gravity, and then I have to give it more force and more acceleration. So like a rocket, right? Like you're saying. But let's be very clear that even though I've got a rocket, I still have to overcome gravity, right? And let's say I launch it with a rocket and I shoot it up. Once the rocket stops pushing on it, now what kind of acceleration do I have? I have negative acceleration. Even though, see, let's say the rocket is launching. It's going and going and going and going and going, and then all of a sudden the rocket stops and runs out of fuel. I was accelerating as long as the rocket's going and I'm pushing more force than gravity, I'm accelerating this rocket, right? But the moment that the rocket, the fuel stops and I have no more thrust, then I'm just then what's happening to the velocity? It's decelerating, and so now I'm accelerating in the negative manner negative direction due to gravity.
So back down.
Yeah, it's gonna start to slow down until it sucks all the velocity out, and then it's gonna start.
Definitely negative that time, or just when it goes
It's
back down.
always negative, right? Because the acceleration is always negative. When I go from my hand to the top, the acceleration is always negative.
So deceleration is negative.
Deceleration is, you could say, if you say deceleration, be careful about it. Be careful how you mean it. Because when we talk about vertical, we're actually accelerating in a negative way, in a negative direction. We are,
So I should say that.
And that's relative to where you start. You know, like negative. You know what I mean? 'Cause, like,
it's a reference frame. It's a reference frame. It's relative to if the positive y is if the positive y direction is positive and that's up, we say that's positive, right? To the right is always positive x, right? Because if you say I'm accelerating or decelerating, the term decelerating is a little I don't like the word decelerating because you're slowing down, but it doesn't communicate that you have a negative acceleration. Because once you reach zero velocity, and you have a negative, you're decelerating, as long as that force is still on you, like gravity, you're going to start to accelerate the other direction. You could be decelerating with the magnitude of your velocity increasing. Okay, so if you use the term decelerating from my hand to the top, okay, well, when the ball's at the top and starts going down, is it decelerating still?
Yeah.
In your definition, yes. Even though the magnitude of the velocity is increasing. Right? It's going faster, but in a negative direction.
Not so much. Okay, so what should I say when it's going back down?
Just always say it's got a negative acceleration.
So it always does.
Well, gravity's always acting on it, no matter where it is.
Wait, so how is it different? How is throwing the ball up like that different from throwing the ball like if it's like arcing? Because are you still going negative, but it goes faster?
Well, what
Is it just a different rate of like
what are you talking about? It goes faster.
the ball?
Which direction?
Horizontal?
See, I think you're starting to get into two-direction motion. You're saying if I throw it purely horizontal or up at an angle. I know where you're going with that. We're going to get there. But for the moment, what I want you to remember. So let me answer your question this way, even though it's probably not your question. Remember when we were outside and I dropped the ball and threw the ball horizontally. When did they land? Same time. So if I know if I know they're going to land at the same time, what must their vertical rate of fall be? The same. So the point being is that the horizontal motion, if I throw something horizontally, even if I throw it at an angle, the horizontal component of that velocity has nothing to do with the vertical component. The vertical component and horizontal are completely independent. So when you say it's faster, what I think you're thinking of, I think you're trying to say, well, it's going to get to, if I throw it horizontally, it's going to get to my point faster than just dropping it. Yes, but that talks about two different motions. Getting from point A to point B horizontally is horizontal motion, which is different than the vertical motion. So I'm dealing with the vertical motion first, and then we'll deal with the horizontal, and then we'll combine them a little bit. Okay?
This is off of this.
No. We won't cover all that before the test.
Like the vertical.
It depends on how far we get. All right. So what I'm suggesting at this point is that, or I'm trying to say is that to your question, Morgan, is that how do you define this? You define this by saying it is accelerating in a negative direction. Okay, it's accelerating in a negative direction. Because if I say it's decelerating from going from my hand to the apex of its height, yeah, that makes sense. It's slowing down. But it's slowing down because of gravity. But after the apex, it's going to start to go down and speed up in the downward direction. By your definition, it's still decelerating. You follow me? Because from my hand to the top, it's gravity. From the top back down is gravity. Well, it's got to be accelerating the same way. So you're saying if I'm decelerating, which is really taking positive velocity away and adding negative velocity, right? Okay. Sort of makes sense. Okay. All right. It's like you have $10, right? And is that the best way? No, we won't even go there. I won't even do that because I'm going to screw that up. Because I haven't thought that through. Okay. So at this point, we're laying out our facts. We know that we have constant acceleration. Why do we know we have constant acceleration? Gravity. Everyone else awake? Yes? Does everyone understand that? We have constant acceleration because of gravity, right? Okay, what else do we know? What other facts do we know? What other things do we know about this object? And we have what kind of motion? What direction motion? Negative, and it's what direction? Vertical, right? It's vertical. It's a down, vertical, okay. Versus horizontal, right? It's in the y direction. We're going to call the vertical the y direction. What is, so what else do we know about this? For problem number one, we know the seconds. What else do we know regardless of the questions 1 or 2? What else do we know about this situation? We know one more thing. Initial what? What? Do we know the initial velocity? It's 0. Nicely done, Grace. It's 0 meters per second. We know that the initial velocity is 0. Very important. Very important. Why is it important? Well, we know it's important because if I am traveling, velocity versus time, and I am constantly accelerating, right? We know that the delta distance is what graphically here?
Constant.
Well, the what area where? Under the curve, right? We know that the distance, the delta distance that we travel, is the area under the curve, right? Correct? Because we know that if I'm doing a constant velocity for time, this is also delta d, right? Right? So the distance from a velocity versus time graph, the area under the curve is delta distance. But this delta distance here, now this is constant velocity, this is constant acceleration, correct? So there's two different graphs here. But when we look at this here, we're starting at what velocity? 0. So the distance under this graph really depends on the fact that it starts at 0, because if it didn't start at 0, and we accelerated, is the area under this curve the same as the area up there? Is this area the same as that area? No. It's actually more. So that delta distance is actually more. So it's really important, Grace's point is that we really need to make sure that we know that it is this initial velocity is 0. Because if it isn't, we have to know this area too, plus that area. Yes, ma'am?
If it's not at, like, if you don't tell us what the starting or initial is, can we always assume that it's 0?
You'll have to look at the question. If I drop the ball or if it rolls off of a cliff, you need to understand. I may tell you, but you'll have enough information to figure it out. I'll give you that, right? Because if I say that the ball has purely horizontal motion off the cliff, then you know that the vertical is 0 because it's purely horizontal. Does that make sense? Okay. All right, because if it's at an angle, you can figure out the components, and we'll deal with that in a little bit. But so be careful about making sure that you know that initial velocity, because your distance is going to change. And by the way, if this distance, this delta d is equal to what? Do you guys remember what that delta distance is for constant acceleration?
Velocity times time.
Well, that is for velocity, but in terms of distance, here's distance. Well, velocity is equal to. No, I'm sorry. You said distance is equal to velocity times time. That's for constant velocity. But we're talking about constant acceleration for the top part of the triangle.
Oh, it's like something squared. It's like t squared.
Look in your notes, guys. Look in your notes. Come on. What's that equation? What is the change in?
1/2 a times change in or delta t squared.
Right. So that for that triangle, the distance is 1/2 at squared, which would be fine if it was just for this guy. By the way, what does this guy look like to you? What kind of graph does this look like? This bottom, this square. It looks like this one, doesn't it? Which is what? What is? Okay. And so the area for the equation for constant velocity, the equation for distance and constant velocity is equal to what?
V times.
Yeah, it's equal to v times delta t, right? And so I can plug that down here because it's the same thing. Delta distance is equal to v times delta t. So I know that my total delta distance is any velocity that I have initial times my delta t plus 1/2 acceleration times delta t squared. All right? Because there's two different pieces of motion going on here. But in this case, do you guys understand that why this equation shows that? You understand that if I'm accelerating, we've proven this equation before, right? We've proven this equation, right? For that distance, we know it's that triangle. But we know that what would happen, here's the thing, right? This represents me starting at a stoplight. I'm at a stoplight, the light turns green, and I hit the gas. That's what this represents. This represents me on the highway going with my cruise control and wanting to pass a truck and now hitting the gas. Okay? If I didn't hit the gas, I would still cover this distance. Period. Because I have a velocity. If I'm traveling 60 miles an hour, I travel some distance depending on the time, right? However, if I do accelerate, I'm accelerating and having more distance on top of my original distance I would have normally had if I didn't hit the accelerator. Does that make sense? So that's why there's two components to this change in distance equation. Then I've got the velocity in time and the acceleration for time. Constant velocity and constant acceleration, right?
It's like 1/2.
A delta t squared. Sorry. So in this problem, if Grace, you're saying the initial velocity is what? How much distance do I cover because of my constant velocity? I don't, because my velocity is what? So 0 times anything is 0. So this portion of my delta distance, right? This is two sums. It's this distance plus that distance, right? The distance I would normally travel with an initial velocity, and the distance I would travel while I accelerate. Well, if I have no initial velocity, I have no other distance that I'm going to travel beyond the acceleration rate. Does that make sense? Carmen, what can't you read?
Change in time squared.
Here, this one?
Yeah.
Sorry. Okay.
Can you see what's on the screen on there?
Okay. Now, blah, 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 blah. Okay. So we've got this, right? So we've essentially talked about the equations that we have. So let's go back to here. I'm going to erase this for a second. You guys ready? Oops. I can undo. Is that, you guys good? Yeah. Okay. So we know that our acceleration, we have a couple of equations for constant acceleration. What's the basic equation for constant acceleration?
Delta V over delta T.
Beautiful. Delta V over delta T. Okay. And the other equation regarding distance, this relates acceleration, velocity, and time for constant acceleration. Because again, we talked about that it's constant acceleration. What's the relationship that we have for distance, acceleration, and time? And we just talked about.
The V equals half L.
Yeah, so delta distance for constant acceleration is equal to what?
Half A times this change in time squared.
Delta t squared, right? Plus our initial velocity times delta t, right? It's a total distance given the constant acceleration and that piece as well. But this guy, because our velocity is 0, our initial velocity is 0, that goes away, right? Because initial velocity is 0, goes away. All right, so now the question is, so we go back to question 1. So we've laying out all our facts. We know that we have a constant acceleration. Due to gravity, our initial velocity is 0. We have some equations that we can use, some relationships, okay? And now the question is, how far am I going to go? What's my change in distance? How far am I going to go from where I stand after 3.2 seconds? So how would I solve that? What relationship would I use? Not distance over time. Distance over time, you're saying velocity equals delta distance over delta time? That equation, or you're saying delta d equals v times delta t? What kind of motion is this for? Is this for acceleration? What kind of velocity? Hold on. How many velocity, do I have a delta v anywhere here? Do I have delta v? No. So that means I have how many velocity values? 1. So if I only have 1 velocity value, is my velocity changing? So do I have acceleration? No. So what is this for? What kind of motion is this for? Beautiful. That's where I want you to get to. I want you to get, you're going to need to be able to do that on your own. You got to say, what is this equation for? What kind of motion do I have? Don't just guess. Don't listen. I first took Latin. Okay, I was in Cistercian for a year. And I took my first year of Latin. I had never taken a language before. I had no idea, and I apologize. Father Matthew, I'm really sorry, but you just were not a good teacher. Okay, I left that class thinking the way to do it, the way to form words is just to know the vocab and just throw an ending on that sounded good. And that got me nowhere, right? I went to St. Mark's and they're like, you're taking Latin again. So I had no idea, right? So don't do the same thing for this. Don't just take an equation and be like, I'm just going to throw it at it. Make sure you know.
Yes,
Don't.
Make an educated guess.
No, you're not making it. You're making a guess, and that's different than an educated guess. What's the difference? An educated guess is thinking about knowing. Hannah, I'm not trying to. I'm not picking you out. I don't mean to do that. You're not. Listen. What you did, everyone does, and I'm trying to make that statement to everybody. Don't just pick an equation And that makes you got to make sure you know what your situation is, what each equation is for, and then at that point, if you know that, the word choose on choose equation doesn't exist anymore. You will know what equation to use. Does that make sense? And I'm not trying to single you out. I apologize. It's not because a lot of people do this. Yes, ma'am. Some other question. Educated guess and guess. Guess. Okay. Let me think. What's a good way? Okay. Pick a number between 1 and 10 in your head. Okay. I'm gonna guess that it's 3. That's a guess. I have no idea. Okay. Tell me what your favorite number is first. 13. So it's either going to be a 1 or a 3. Which one was it? It wasn't. Okay. Well, I could be wrong, but at least it's an educated guess. I'm using some level of knowledge to back it up. Now, her educated guess was velocity, but I want to go through the whole process of saying, okay, why is it velocity? I had a reason why I chose 1 or 3. Because you follow me? What was it, by the way? 7? 7?
I knew the jump.
Okay. All right. Okay. So, given the scenario, I've got this equation I can use. I'm going to get rid of this one because we can't use this one. Why can't we use that one? Constant velocity. And what kind of motion do we have? Constant acceleration. Okay. So this is our change in distance for constant acceleration plus our initial velocity. Initial velocity 0. Yo, yo, yo. So we have delta distance. So we're asking how far we go after 3.2 seconds. Now notice I have a relationship between my distance, which is what I need, the acceleration, which is what I know, and time, which is what I've been given.
So do you need the other part of that?
Well, if I had an initial velocity, yes. But my initial velocity, you still need this part. What's my initial velocity? 0. So it goes away in this case. The difference between delta distance equals 1/2 a delta t squared and delta distance equals 1/2 a delta t squared plus v naught delta t. The difference is this. The first one, I said to drop the ball. The second one is I throw the ball. The second one is I throw the ball down. Right? But you see the difference? The difference is I drop it versus I give it an initial velocity. It's gonna. Yes, it's a 9 ball. Does that make sense? Does that make sense?
Yes.
That's why you're gonna use it. Yes.
So even though we're not using the initial velocity on the, do we still use the delta t?
Well, 0 times delta t is what?
It's 0.
So that goes away. So now you're just left with this.
So you're not gonna have. Well, okay.
You follow me? Because again, this is the change in distance that you have from constant acceleration plus whatever distance you would have gone if you stayed at that initial velocity. Think of the car example. I'm either this part right here is me being at a standstill at a stoplight, hitting the gas to accelerate for a certain amount of time. I'm going to cover a certain amount of distance. This scenario here, velocity and time, is me going on the highway, cruising at 60 miles an hour next to a truck. Okay? So I'm going to cover a certain amount of distance because of 60 miles an hour, for an hour I cover 60 miles, right? But when I'm next to a truck, I want to pass it. I'm already going that velocity, and I'm going to cover distance because of that velocity. But now when I accelerate to go past the truck, I'm going to cover even more distance than if I didn't accelerate. Does that make sense? So you have both terms in here, but you need to know which one, you need to know the values, and a lot of this will take care of itself. So if you've got an initial velocity, then you know to put it in there. If you don't, then it'll go to 0, and then you'll have to stop. And look, if I have acceleration 0, then what happens? My change in distance is equal to constant velocity, right? The alternate reality equation. Woo. Okay. All right. Okay, so our change in distance is equal to 1. So at this point, we've got change in distance is equal to 1/2 at squared because our other term goes away, right? We've got this guy right here. All right. And we know our delta distance, don't we? We're looking for a delta distance. So delta distance is equal to 1/2. What's my acceleration term? Okay, very important, guys. Negative 10 what? Meters per second squared. Don't forget the negative term. It's very important. I'll show you why in a minute. Times are what? Times what? Our delta t, which is what? 3.2 seconds, and all of that squared. Notice the seconds is inside the squared term. Because not only am I squaring the 3.2, I'm also squaring the seconds. Because the units are getting squared. It's like square meters or square feet. Right? I'm squaring both of those. So I'm going to get negative 5, because I'm going to say 1/2 of 10, right? 1/2 of negative 10, meters per second squared times, and what's 3.2 squared? 3.2 squared is 10.24 seconds squared.
What happened to the other part though?
Which part?
The part with the change in time.
This one
Not
here?
squared.
This one? Remember, okay, so this is plus initial velocity times delta
it's
t,
times zero.
because it's times 0, right?
We did this on Thursday. It was just like,
We didn't do it on Thursday. We didn't do this
oh right.
Right, we did a horizontal thing. We did constant velocity on Thursday. We went through the first one. Okay? So now look, I do it this way. Look at this. Look, I'm doing it this way because I want you to see the units that cancel out. Okay? Ultimately, this is equal to delta distance. Delta distance, now look, I'm going to cancel my s squared and my s squared. You guys see that? Second squareds cancel. Cancel.
10
because this 3.2 squared. So 3.2 seconds squared equals 3.2 squared times second squared. And 3.2 squared is 10.24.
Oh, 10.
Sorry, 10.2. Okay? So now I'm going to have 5 times 10.24, but it's negative, right? So it's negative 51.2. Negative 51.2, and what I'm left with is meters. Now, couple of things. Number one, I've done the problem, and I've calculated the numbers, but I've carefully kept my units inside this. I've carefully kept track of my units. Why? To do what? And to know that at the end, I'm looking for a distance, I better not get seconds or seconds squared or meters per second or something else funky. I'm looking for a meter, right? And it's kind of a check. Doing your units is like a check. Did you do it right? Okay? I think I was working a problem in this class or some other class, and I had flipped in my head the equation. I just dyslexic it and flipped over the equation. And I was getting like meters squared per second squared, but I was looking for meters or something. And I was like, what did I do? And I realized just from the units that I did something wrong. And I went back to go check. So this is powerful stuff to use as a check for yourself. Okay? The other important thing, what sign is this number? Negative. Why is it negative?
Let's go down.
From where I started, I'm going down 51.2 meters. Now, that doesn't mean that I'm 51.2 meters from this point up. It's from here down. So it assumes that this is y equals 0 right there, not here. You guys follow that? You might say, well, the ground is 0, but really, remember the whole electric thing, potential, what's all relative to ground? Well, here we go again, right? This is now 0 relative to ground, so we are going to go down to here. So it's going to be a negative 52. So the y here is equal to negative 51.2 meters relative to that start point. Now, relative to the ground, this point is 51.2 meters. Carrie, you good? Okay. Does that make sense? Just making sure you be careful of your signs and be watchful of your relationship there, your reference plane. Does that make okay?
Yes.
All right. Number 2. Let's go to number 2. I forgot there was number 2. All right. What's number 2? Okay. So how long does it take? Oops. Oh, undo that. So how long does it take to do what now? 52 meters. Oh, so it was pretty close to where we were, isn't it? It's pretty close. So let's take a look at this, right? I think I guessed at that number. I just randomly put a number down. Woohoo! Give me that. So I know. So in this case, what equation could I use again? This equation, right? Shh. What's my initial velocity again? 0. Still 0. So my delta distance still equals 1/2 a times delta t squared, right? So, Hannah, up here. Guys, both of you guys, focus. Okay, so what is my change in distance for number 2? What is my change in distance for number 2?
So do you, what? Where have you seen him? The wooden guy. See, Mr. Ray? You see why I'm closer to her?
Okay, let me finish this. We have 5 minutes. So delta distance equal to 1/2 a times delta t squared. Okay, what's my change in distance for this question? Negative 52 what? Meters. Okay, equals 1/2. What's my acceleration rate? Negative 10 what?
Meters per second squared.
Yes, guys, don't get lazy on me. I will count off. Per second squared. Times what's my delta t? Oh, that's what I'm looking for. All right. So now I'm looking for my delta t. So delta t squared, exactly. That's what I said. So delta t squared is equal to negative 52 meters divided by 10 meters per second squared, negative, times 2, right?
You just like reverse it all.
Yeah, you kind of like do a little mix master.
Why can't you just multiply that out and divide it?
You can. You can. You want to do that? Let's do that. I put the half as the 2.
A little bit.
All right. Oh my God. No, I'm just showing you where each term goes. This is 2 steps in one. This is 2 steps in one versus doing it. This is not one by one. This is 2 steps in one. This is two steps in one. We're moving along.
I'd rather not confuse us.
Okay. So equals 52 divided by 5. 52 divided by 5 seconds squared equals my delta t squared.
Yes.
You guys see that? Guys, you're goofing. Listen, you're goofing off, and it come test time, I'm
It's okay. 52 divided by 5 and then s squared.
s squared, right? Because again, this negative 52 meters over 1 times, because if I'm dividing this by negative 5 meters, it's really times negative 5 meters seconds squared. So that way my meters cancel, I'm left with seconds squared. That's why I have seconds squared there.
So then the t squared and the s squared cancel, so you just get s.
No, you have to square root both sides.
Oh, yeah, that's fine.
Well, let's make sure, let's be careful. Yes. Right. So now what you got to do is you have to say, okay, so delta t equals, I'm doing Mr. T. Delta t equals the square root of 52 fifths, right? Seconds squared.
So what? Your head.
I'm sorry, my head's big.
Change t.
So 52 divided by 5, square root that is 3.22.
So it's the same as.
It was, I randomly picked the same number. I apologize. 2.22. 3 equals 3.22 seconds. Does that make sense? You there? Guys, listen up. Listen. This is going on the YouTube channel. Everything we're doing is on the YouTube channel. You need to go and work these problems again. You need to you need to watch the video, work the problem on your own, be able to do this on your own. That's the goal.
Become spiral on YouTube.